Hello and welcome to Lab 5. My name is Sam Kurtzinger and today we are going to be modeling friction. How exciting. So today I'm going to try to predict the motion of a ball as it rolls to a stop. Our goal is to estimate the total distance of the ball roll. First we will load the video into a program called Tracker to record the ball's changes in position. Next we will then model the motion using Python, using initial conditions determined in Tracker, and we'll find a model of that motion and then compare it to our video data. You will see that with just a few equations and physics fundamental principles, a ball can accurately be modeled. So let's go over the major physics concepts at work here. The first equation is Newton's second law. This equation basically calculates the new velocity from an old velocity, initial velocity, by adding the initial velocity to the quotient of the net force and the mass of your object times the change in time. Our Python code is effectively going to integrate by calculating this equation hundreds of times for us. So the next equation is to calculate what's going to be our net force, the force of friction in this case, which is the coefficient of static friction, or it's the coefficient of static friction for our ball times the force of gravity on the ball. So here I have the video loaded into Tracker. We go and press play. You can see the ball is rolling in the negative x direction along the purple x-axis there. This blue calibration stick lets the program know about how wide the ball is to help us accurately record the distance. On the right here you can see the points being plotted. This is the x position of the ball, and you can see the x and y positions over here. Notice the ball initially starts out with an initial velocity pretty constant and slowing down, and finally it comes to a stop right there. So now we're going to translate our physics into Python code. Here I've got the ball's mass, ball.m set equal to around 0.05 kilograms. Ball.pos represents the ball's position. Ball.vel, you can see it starts at the origin, 0, 0, 0. Ball.vel is the velocity. We have initial velocity of negative 1.39 meters per second. Gravity, g equals 9.8, that's the gravitational constant. UK is the coefficient of static friction. I got this value basically through empirical methods, trying it out until it correctly modeled our data. And then the force of friction here is calculated simply by multiplying the ball's mass times gravity times our coefficient of static friction, or kinetic friction, excuse me. So we'll be creating two different models of our ball rolling. One will include the force of friction and one will include no net force. So this snapshot here has Fnet equal to 0. So this is the one with no net force. This line above it here, Fnet is set equal to the force of friction we calculated in the previous slide. And that, when we run that net force, will account for friction. So anyway, this is Newton's second law that we mentioned earlier. The final velocity equals the initial velocity plus the net force over the mass of the ball times the change in time. And then the position is updated here. So the final position equals the initial position plus the ball's velocity times the change in time. Now I'm going to show you the Python code running. This is the code that accounts for friction. So we're going to go ahead and run it. You'll see the ball starts with initial velocity and then it slows down, and you can see, if you remember from the graph earlier, that this model is very similar looking to the one that was in Tracker. This next time we run it, we're going to not account for friction this time. So you'll see when we run it, the ball starts with an initial velocity and it keeps going straight and it keeps going straight. You can see this line is constant. There are no forces acting on the object, excuse me, and so the velocity is just kind of in a straight line, constant. So let's talk about the results. Here we've got the ball's position plotted against its time. So the orange line here is the model when we did not account for friction. The red line is when we did account for friction, and then the blue line is the tracker data, so the data from the actual ball rolling. You'll see that when we account for friction, the calculation is pretty close. This discrepancy, this gap in between the two, probably comes from movement along the y-axis. So when we rolled the ball, it kind of rolled not just perpendicular to the camera, but it kind of moved to the right, and that is probably the reason for that discrepancy there. But had the ball moved in a straight line, it probably been pretty close to this red line here. So you can see that when we account for friction and just using Newton's second law, we can accurately predict the motion of a ball rolling. Thank you very much for watching.